Ooh, fresh coffee is always so good. Yes, I am drinking coffee at what is 9 o'clock p.m. at my time. I hope y'all are enjoying your mornings or afternoons or whatever time it is for you. Ooh, leaderboard has changed for today. So we've got Talk Climb and Anonymous User, first and second, as usual. But we've also got a new third place. So Frobiak is how I'm going to pronounce that. Ekes out Boley for third with not that much of a lead, I suppose. Of course, it's always interesting to see how many people we have still sticking with because the percentage of people that complete all the problems, or at least one part of both days, always drops. So we're at 48 people right now, which is pretty good. And we've got a fair few, another like 25 up in the 20s, which I really love seeing. I really love seeing that people are not just doing them, but also succeeding at it. And mostly I just love seeing people stick with it more than anything else because it's tough to get through all 25 problems, even just the part ones, even if you look up some of the answers. So congratulations to everybody that's been working on these problems. Lucky number 13. You climb the hill and again try contacting the elves. However, you instead receive a signal you weren't expecting, a distress signal. Well, maybe the elves shouldn't have ran off. Maybe they should have hung out and waited for us to come up. The packets from the signal are out of order. The puzzle input will need to be reordered. Your list consists of pairs of packets. Pairs are separated by a blank line. You need to identify how many pairs of packets are in the right order. For example, yada yada. It looks like we always get a pair of packets, which is kind of cool. I have no idea why they're nested. Packet data consists of lists and integers. Each list starts with open square bracket, ends with closed square bracket, and contains 0 or more comma-separated values, either integers or other lists. So this is sounding like an enum to me. It's an enum where it's either a list or an integer. Each packet is always a list and appears on its own line. So the root is always a list, and then going into that is always either a list or a number. Oh, I remember these from last year, actually. When comparing two values, the first value is called left and the second value is called right. Then, if they're both integers, the lower integer should come first. If the left integer is lower than the right integer, the inputs are in the right order. If the left integer is higher than the right integer, the inputs are not in the right order. Otherwise, the inputs are the same integer. Continue checking the next part of the input. If both values are lists, compare the first value of each list, then the second value, and so on. If the left list runs out of items first, the inputs are in the right order. If the right list runs out of items first, the inputs are not in the right order. If the lists are the same length and no comparison makes a decision about the order, continue checking the next part of the input. If exactly one value is an integer, convert the integer to a list which contains that integer as its only value. Then retry the comparison. For example, if comparing a list and 2, convert the right value to a list containing 2. The result is then found by instead comparing the list of zeros and the list of 2. Using these rules, you can determine which of the pairs in the example are in the right order. Pair 1, compare these two. 1, 2, 3, 4, 5. Both 5 of them. We only get to comparing the third position before we have a valid comparison. The left side is smaller, so the inputs are in the right order. For pair 2, we've got 2 lists. We first have to do 1 and 1, which goes in again to do 1 and 1, which returns nothing. So there's nothing we can do there. We go to the next element, which is list and 4. We convert 4 to a list, and then retry, which gives us 2 versus 4. I feel like we can always skip the list. If there's a list and a number, we can always skip creating the list and just do the first one versus the number. That seems right to me at this point anyway. We'll see. Left side is smaller, so the inputs are in the right order. 2 is less than 4. Pair 3, list of 9 and a double list. 9 versus list, mixed types, 9 versus this. 9 is greater than 8. Inputs are not in the right order. So we're just identifying which ones are and are not in the right order. Do we have all of these in a list somewhere I can copy paste? I guess it's all of this, right? Copy, and then we can come back in here to figure it out. So here's our input. The parser feels like it's pretty easy to write. It's either just an enum or a list, or a number or a list, sorry, separated by commas. What are the indices of the pairs that are already in the right order? First pair has 1, second pair has 2, and so on. In the above example, the pairs in the right order are 1, 2, 4, and 6, the sum of which is 13. So I feel like from my perspective here, I want to write an enum for either a list or a number, and I want to write a comparison implementation that will compare them together. Comparison implementation for the enum specifically. Okay, so let's get started with that parsing then. and then we'll figure out how to do the comparison. So thinking about this, we get like a U32 for the numbers and a delimited by square brackets separated by commas. I think it's separated 0. So for parsing, the interesting things for me are the edge cases. So like empty square brackets, what happens there, and so on. What do we call these? I forgot what we call these already. Packets, packet lists. We'll call this pairs. We'll take a string slice. We'll return our I result, which is a string slice, and it's going to be a vec of pairs. I think that's right. Actually, now that I think about that, I don't know if that's right, because each of the elements is going to be a vec anyway. So I think pair just gets left and right. Like this could be a tuple, basically. We might change this as well. This isn't an enum, this is a struct because we have field names. We have an enum that's a packet that's either a list, it's a vec of packets, or a number, which is going to be a U32. So fully pairs is going to be separated list, 1, tag, new line, input on the end. This gives us each of the 2 packets to read. We always have a list at the root, so not terribly worried about that. So separated list 1, because 1 always has to be there. New line, and then packet. That feels right. Forgot a little bracket there. Separated list, tag, import tag. What else do we need? New line, probably I don't have imported. So this is actually a vec of pairs. And this actually I think will be a little bit more specific about rather than doing separated list. So there is a separated pair. I forgot whether it was separated pair 1 or not, but I guess it wouldn't be 1 because it's not a list. So we've got a separated pair, and it is packet, new line, packet. And I'll map that P1 and P2 into a pair. Separated pair needs to get brought in. This is just a vec of pairs. Okay, I was right in the first place. Function packet, input, string slice, I result, string slice, packet, and then we get either a list or a number. So I guess we do an alt here because that makes the most sense for enums, of course. So we could do a delimited, and then in the middle, we do a separated list 0 because there could be nothing here. And we do a tag of comma and a nom character complete U32. And I'm just going to bring all these in. So if you're not familiar with what I just did, I just pulled them all in via Rust Analyzer. So now they're all being pulled in the use statement or the use item. We do have to pass in input here. There's something wrong, so I'm going to check it. Cargo watch X test. Alt is not implemented for impl function mute. That usually means that we didn't pass the input in correctly. I think what that'll mean in our case is that, alt. I didn't write the second alt. That's what we did wrong. So it's either delimited or, so tag comma, and this is going to be packet actually. So it can be recursive. And then the alternative is a number, right? And these currently return very different values. So I assume that that's the error that we should be hitting. Yeah, expected packet found vec. So separated list 0 delimited dot map, because delimited is a parser. And this is just going to be a vec. This will be a packet list in that vec. And this will be dot map number packet number num. And that should fix our errors, because from this alt parser, which is either this delimited or this U32, we have to return the same type. In this case, we're returning packet from both of them. So this delimited will carry out the parsing as usual with separated list 0, looking for packets delimited by commas or packets with commas between them. And whenever we get that list value, if there is one, we put it into a packet list. And then it goes down and goes down and goes down. Same thing for the U32. Whenever we get a number here, we will map over it and turn it into a packet number. And this allows us to do our comparison on packet at some point. So we get pair list on that. We debug out pair list, but it doesn't work because I didn't debug derive. I really just said debug derive, didn't I? I meant derive debug. Sometimes words just get in the wrong order. So holy, we get a lot of stuff because there is no pretty printing here. So we get the pleasurable experience of printing out all of this stuff. So let's check. 11311, 11311, list 11511, list 11511. We should probably pluck this in for a test. So I'm just going to legitimately copy the output there and write another test here. And I don't really want to deal with the white space, actually, now that I think about it, which debug gives us quite a bit of. I think we can do equality though. So instead of using this as a string, we're going to dump in this whole built up structure. for all of the pairs. The output from this, if we're wrong, is not going to be great. So if we are wrong, I probably will chop this test up, but we have to do the same thing we just did here, which is run our parser on the input. We have to unwrap it. We have to get the first value because that's the one we care about. And then this is going to give us a vec. So we're going to get a vec here, and nothing is in scope, as you can see from scrolling down this large list of issues, because none of this is available. So I'm going to make everything public so we can access it in our test. Oh, that might not have actually been our issue. This is going to be a pair. These are going to be numbers. Oh, interestingly, we have a comma in all of these. That's probably not great. I think those commas are because of the way it was formatted in the output. So we are going to, inside of this function, do use packet star, and then we get to avoid actually doing packet : list. All of these lists are going to have vec inside of them. So I'm just going to select them all and do that. And I just need to remember that this is affecting one that is way up high. That is untrue. So this is the one that I need to delete. And then I need to delete this one. And then binary operation equality could not be applied to vec pair. That's fine. I think doing partial equality is enough here. We do need to do capital I input for our test input, which is this string right here. Part 1 works and part 2 works are now incorrect. Let's get rid of this debug now that we don't need it. So parser works is okay, and part 1 works and part 2 works. Both are still failing because we have the to-dos in both of them. So that leaves us with making sure that we got the right output. So this first pair is correct. I don't like having those commas there though. I don't think any of them are actually syntactically relevant, so I'm just going to remove all these commas solely because it's harder for me to read. Okay, so the first pair is fine. We're good. The second pair is a list with a list of 1, and then a list of 2, 3, 4, and a list with a list of 1 and a 4. So a list with a list of 1, and a list of 2, 3, 4, and a list with a list of 1 and the number 4. So this one's good too. This is a list of the number 4, and then a list of 876. That is correct. And we've got basically the same thing for the 4s here. So we've got a list of 4, 4, 4, 4, list of 4, 4 with 3 4s. So this one is also correct. We've got a list of 7s and a list of 3 7s. That is correct. That looked weird. I thought it was wrong. An empty list and a list of 3. Yep. This is the one that I'm concerned about. List, 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 and list, list. So we've got 3 lists and 2 lists. That is correct. That was the one that I was most concerned about because it felt the most edge casey. So we've got list with a number with a list. So these should match up to 5, 6, and then 7, 0, and then have 8, 9 at the root. So vec 1, vec 2, vec 3, vec 4, vec 5, 6, 7, and then 8, 9 at the root. Vec 1, 2, 3, 4, 5, 6, 0 with 8 and 9 at the root. So these all look good, actually. All of them look good. I'm just going to collapse them so that we don't need to see them anymore. But that's just a code fault. So lines 89 through 205 are just that test. But we look good. Our parsing is solid. So to process part 1, we parse into these pairs. The pairs struct is a left and a right, and the packet struct is a list or a number. The pairs are separated by double new lines. Those pairs, so we have then we have these two, for example, right, are separated by a single new line. So we've got a separated pair parser with a packet on the left, packet on the second line. We map over that to create the pair struct. Each of these packets is what we'll call a recursive parser. So we get alt, right? So we're going to parse a packet. Think about this as a packet. It can either be another list or it can be a number. Those are the two packets that we can return. The finish case, the final case, right? If we're recursing down, the final case is we're going to land on a number somewhere. So think about this number probably first, and then we map over that to return a packet from this one if it succeeds. This is the recursive part. We do a parser that is a delimited parser that has a tag on the left and a tag on the right of open bracket, close bracket. We do a separated list 0 inside of that array. So there could be nothing in here. We could have an empty open bracket, close bracket. That's what the 0 does for us. Otherwise, we're looking for a packet, and if there are multiple packets in a row, those will be separated by commas. So this works out for us. If there's only one item, we just keep looking for another packet inside of the two brackets. So in this case, for example, we look for our first packet, we match on the first open square bracket here, and then we look for another packet as the first element, which gives us the second list. And we match on the third one here, and then we fail both of those next parsers. Well, we don't fail both of the next parsers. This succeeds. This inner list succeeds. It succeeds with 0 elements inside of it. So we get 3 lists here and the final list just doesn't have anything inside of it. So there you go. Recursive parsing in Nom. I'm curious to see how y'all did the parsing. So please do let me know in the comments. Also note that when you share links to your answers in the comments, the ones that link to like GIFs or stuff like that are all getting like auto removed by YouTube. I've seen this on a number of different videos. People are very confused as to why their comment that they typed out doesn't have, like, it got like removed or deleted or whatever. This is because YouTube is auto removing links to like GIFs or like paste bins and things like that. So just be aware of that if you're going to show your share your code. I don't want you to type a comment and then have all that work just removed by YouTube. So we've got our pair list here, and it's going to be pairlist.iter.map for sure, because we just need to do the same operation to all of them. So we can just destructure the pair here. We've got the left and the right pair. So if we aren't going to worry about the logic yet, I just want to know, once we apply the operation, which one wins. So packet data consists of lists and integers. Yep, conversion to a list, etc. It's kind of like mixed up the equality logic with the process of checking. So if the left integer is higher than the right integer, the inputs are not in the right order. Otherwise, the inputs are the same integer, continue checking. If the left list runs out of items first, the inputs are in the right order. If the right list runs out of item first, the inputs are not in the right order. So I guess we could abuse ORD here, the ORD instance, to be able to write like a partial ordering, which I think will be valid compared to we've written a PartialOrd instance in the past, but the PartialOrd instance we wrote on like day, I don't know, 6 or whatever, wasn't technically valid. It was just kind of a hack. If exactly one value is an integer, convert the integer to a list. So if the left value is bigger, always it's the right order. If the left value is smaller, it's the wrong order. If the left integer is lower than the right integer, the inputs are in the right order. This is the same phrasing, right? So if the left integer is lower, we're in the right order. If the left list runs out of items first, we're in the right order. If they're equal, we just keep continuing. So I think this matches. We can do an ordering instance on this. If the lists are the same length, continue. If exactly one value is an integer, convert the integer to a list, yada yada. So I think we're good to do left comp right. Comp being a trait that we don't have in currently, or that we just can't call yet. You know, it would be really funny if we just derived it and it just worked. The likelihood that that happens is so just absolutely not going to happen. But at the same time, I really just want to see what happens. So we're gonna take a fun break for a second, and we're gonna pretend that we have this comparison function already. So I'm gonna enumerate here to get the indices, whatever you want to call those, I and pair, and then we're gonna sum this, and we're gonna sum this into a U32. And which index do we return? I forget. What are the indices of the pairs that are already in the right order? Should be 1, 4, 6. So already in the right order is I. I think this is panic. And then greater is 0. I guess we could filter map, so we don't need to panic. Filter map, sum I. I think I'm still going to panic there. And this is going to be none. And this is all going to sum. And then we'll toString. And we have a problem because the trait sum usize is not implemented for U32. This can be usize. It doesn't, if I can type it, it'll be usize. It doesn't matter to us which integer type we're using here, really. Okay, so our cheap trick didn't work. I didn't really think it was going to, but it would have been really funny internally to me if it did. 0, 1, 3, 5 is what we get. Oh no, did that actually work? Hang on. What are the indices of the pairs that are already in the right? The first pair has index 1. Oh no. Yo, this is not good, y'all. Because this is going to be v plus 1, and then we're going to sum it, and it's going to be the right answer. This is the right answer. We didn't have to write the equality logic at all. Oh, that scares me. That scares me. You know why that scares me? Because the puzzle input is going to have some special piece. Oh no. Oh, I'm scared. I'm scared. Let's do cargo run. Oh no. Oh no, 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 no. Oh no. That's not the right answer. Okay. We just got lucky on the test, y'all. We just got lucky on the test. That is actually hilarious, though. So for the tests, if all we do is derive the ordering instead of implementing it ourselves, for whatever reason, all of this evaluates the exact way it's supposed to. It doesn't for the actual input, but it does for the test input, which is absolutely hilarious to me. We're not supposed to count equal, right? Actually, it never panics, so we never hit equal. We never hit equal in either situation. Oh, I would have been so... That would have been so funny if we could have just derived it and it worked. Okay, but you see what we're doing now, regardless. We need to have some PartialOrd implementation because that's where our logic is going to live. That enables us to run CMP. So we're comparing. Oh, okay, so we parsed all the pairs, right? We're iterating over them and we're enumerating. We do a filter map with the index that the pair is at, and then the pair itself, which has a left and a right, which is the top and the bottom. We match on a comparison. That's what CMP is, compare. Left, compare, right. If the ordering, because ordering is an enum, because when we compare things in Rust, what we get back is an ordering enum with less, equal, or greater, not like in other languages, 1, -1, and 0. We can match on that enum, and if it's less, then we want to return the index because we're supposed to be returning all of the indices that are in the right order already. If it's equal, we need to panic because I don't think that should ever happen. According to the problem, according to our test input, and according to our real input, we actually have never had an equal happen. And if it's greater than, we don't care about it because it's out of order. So we just return none. So filter map will continue with all of the items that we give it that are sum, and it will get rid of everything that we return as none. So then we map over these because the index, if you read the problem, is 1 indexed and not 0 indexed. So our enumerate starts at 0, but our answer for the sum needs to start at 1. We sum that into a usize and we toString it and return it. So this logic doesn't need to change for process part 1. All we need to do now is write a different ordering implementation. So let me do this because I would like these to be a little bit less verbose. And I'm going to do use the, that's the wrong thing. What is it? Standard comp ordering? We don't have anything that's named this already. So I'm going to do a : : star. And what that's going to do for us is let us access the variants by their short names. I also love this enum because we don't have to think about whether less than or greater than is one or the other caret. So we need to implement PartialOrd. Think we can avoid ord itself, but we'll check the traits. So let's start running our tests. We do need to ignore the part 2 tests because I wasn't doing that before. It does look like Packet needs to implement ord, interestingly. So let's see. So we've got PartialOrd, which is partial CMP, and this is less than or greater than. If we implement partial compare, we get less than or greater than. And if we look at ord, because there should be a total ordering here, if I'm reading this correctly. If we do ord, we can implement CMP, which is the function that we used, which gives us a max, a min, a clamp, and I think that's fine. I think we can do a total order here. Here's an exact description of, because we derived ord, this is the equation that we were using before. So if you're interested in that, you can go to this page, find the lexicographical comparison under the ord trait. So ord requires that the type is also PartialOrd and totally equal, which itself requires partial equality. I think equality is one of those things where we don't actually implement equality. This is just kind of like a note to the compiler that we do have a, a total equality. So if we have EQ, that means that we can do A equals A equals B equals B equals A, and A equals B, B equals C implies A equals C, which is all true for us. But we don't actually implement equality. We implement partial equality. So we can implement partial equality here. I'm 90% sure that if we impl ord, then we can derive PartialOrd because this will be our implementation. So for partial equality specifically, we have to match on self and other. This implies, interestingly, this only wrote out 2 options for us: self-list to self-list and self-number to self-number. So I believe this is our full match. We still need ord technically. So let's do impl ord while we're here. Implement missing members. It'll just be a to-do, so it'll fail. So for equality, basically we match on self and other. If they're both lists, then we can use the list equality, so equality between vecs. If they're numbers, we can do number comparison directly. If it's a list and a number, we have to wrap the number in a vec and then do the comparison. If it's a number in a list, we have to wrap the left-hand number and do the comparison. And then we have to implement ord still. So we get self and other for ord. and we can end up with one of these four. So it's either list list, list number, number list, or number number. I'm trying to think about what happens if two vects are not the same length, but they have, like if we have a let A equals vec 0, 1, 2, for example, right? And let B equals vec 0, 1, 2, 3, 4, and we do debug A equals B. We run this, we get A equals B false, which is accurate. But if we do A compare B with the appropriate type, then we get less. On the left, B compare A dies to existing for too long. Okay, so B comp A got killed by the web server too many times, so I'm just checking A comp B again. Think that the Rust playground is down? Yeah, Rust playground is down. That's really unfortunate timing. I wonder if they're updating or something. All right, well, we can take this and we can do our own test. For bin, I'll just do scratch.rs, and we'll have this, and we'll have fn main with the same code in it. I'll do cargo run bin scratch, and we get less. So A comp B is less. B comp A should be greater. If we have the number 2 here, B is still greater, and that's a bad test. So let's do this, and hopefully we get less. We do get less. So it does compare element by element, and it does compare by length at the end. So if we do something like this, B is still less than A. So I think we're good to just let this ride on list equality, or rather list ord, A dot comp B. Also, if it's numbers, we're free to let it ride. So we've got A and B, and we can do A comp B. If it's a list and a number, we need to do our trick up here again. You can totally tell which code was written by me because I'm using A's and B's, and which code was automatically scaffolded out by Rust Analyzer, which uses L0 and R0. So if we do all of that and we cargo test, our tests pass, but our tests were also passing before, so that doesn't guarantee us anything. But what we have done is implement ord, and we've implemented partial equality for packet, and at least now we have a basis to start doing the rest of the logic. This gave us a different answer though, so 5506. So let's try that answer, and that is the right answer. So what did we do here? We parsed out our pairs. Parsing out our pairs I went over earlier, so I won't go over it again. Look at the chapters if you want to recap on that. But it's a recursive parser using nom. So we get the pair list. The pair list is a vec of pairs, not a vec of fruits. We iterate over that pair list and enumerate to get the indexes or indices. We filter map over that with the index and the pair. We take the left, we compare it to the right. If it's less, we return the index. If it's equal, we panic because that shouldn't happen as far as I can tell. If it's greater, we return none, which filter map will drop. Then we map over them to do +1 because the score that they want us to use is 1 indexed and our enumerate is 0 indexed. We sum that, we give it to a string. The reason we can do left comp right is because we have derived PartialOrd and equality. Equality is a marker trait, is what I'll call it. It doesn't have any extra functions or anything like that. It's just a signifier to the compiler that it's a total equality. PartialOrd is something that we derive, and then we implement partial equality and ord for packet. Partial equality is for testing to see if two things are equal. In this case, we need that to know if we should continue on. The first two here, list versus list and number versus number, we rely exactly on list equal list and number equal number. Because we can do that, we can just rely on Rust. If we have a list and a number, that's when it gets a little bit more tricky. We have to take the list and then we have to wrap the number in a list so that it can be compared to the other list. So because these lists are references, so it's a reference to a vec in a packet, I chose to also reference the vec with the packet that we have inside. We do need the number to be the actual value and not a reference though, because in our packet definition up here, these U32s are numbers or U32s and not references to U32s. So we wrap them, and then we basically do the same thing for the ord implementation. We have self and other, so we have two values. They're either going to be both lists, in which case we can rely exactly on the comparison between two vectors, or they're going to be two numbers, in which case we can rely exactly on the comparison between two numbers, or they're going to be two different variants, basically. It'll be a list and a number, or a number and a list. If it's two variants, one is a number, one is a list, we need to wrap the number in a list and then do the comparison. And then we're good. So in all not that much code, we get our total comparison equality situation. Now, hopefully part 2 doesn't destroy all of the work we just did. Now, you just need to put all the packets in the right order, disregard the blank lines in your list of received packets. The distress signal also requires that you include 2 additional divider packets, 2 and 6. Using the same rules as before, organize all the packets, the one in your list of received packets, as well as the 2 divider packets into the correct order. Okay. For example, the result of putting the packets in the correct order is this. Let's just snag this, I guess. I don't know what I'm going to do with that. We would have to implement display to get this output is what we would need to do. Afterward, locate the divider packets. To find the decoder key for this distress signal, you need to determine the indices of the 2 divider packets and multiply them together. So first packet is at index 1, second packet is at index 2, and so on. In this example, the divider packets are 10th and 14th, so the decoder key is 140. What is the decoder key? So this should be, if everything works out for us, pretty simple. We do need to start running this test. Let's do a watch test here. Take the same code that we just had. Now we parsed these pairs. We do need to map over these in a different way. So we'll iter, we'll dot map, we'll destructure the pairs, and I'm going to flat map this and return an array, which will iterate over them. We don't need to do this comparison anymore. We don't need to do that or this or this or that. We're just going to collect. This is going to be a vec of packets. What did I do wrong? From iterator is not implemented for vec of packets. Oh, this is a vec of a reference to packets. Interesting. Packets.sort. We need packets to be mutable to sort it. Packets.iter.find. What are the 2 divider packets? 2 and 6. This is packet list, packet number 2. So I think that's divider packet number 1. Packet list, number. And instead of guessing at the issue, let's go read the compiler error. The trait partial equality is implemented for packet. Required for triple shared reference to packet to implement partial. Oh, did I leave a... Okay, let's check to make sure that that's... let's do this, I guess. You know what I didn't do? These actually have to be vecs, don't they? So that's a vec. This is a vec. Can we not triple destructure? Well, it's double, and then I guess I will shared reference this instead. So that finds the first one. We also need to find, this is going to be index 2, and this is going to be index 6, right? And all we're going to do here is enumerate on both of them. So this will give us index 2 times index 6, 2 string. This is .0 and this is .0 because it needs to be the indexes. I think the indexes need to be added. So I modified the find because I added enumerate. These all have the index now, although we don't use it in the find. These are both options, but if they don't succeed, then we're in trouble. So we'll unwrap that. Data moved here, moved because packet has type packet, which does not implement copy. That's totally fine, actually. I don't really care about that. But the other option, I guess, is can we even write a triple reference like that? This is gonna look so weird. So we were unable to find, let's see, number 2, interestingly. So let's do, oh, you know what I didn't do? I didn't add 2 and the other one. I'm gonna call this packet 2 and I'm gonna call the other one packet 6. And I am going to, in this, we're going to have packet 2 here equals this. This is going to be the same thing for packet 6. And this is going to be a references issue because this needs to be a reference and the other one does. That's why I defined them up there instead of in here. So we end up with 40, but that's not the whole story yet, actually, because we need this plus 1 and this plus 1. And now we're at 54, which is not what I want to see. So let's do index 2, index 6. Let's see what we get. We get 8 and 5, which should be 6 and 9. First packet index 1, second packet index 2, and so on. In this example, the divider packets are 10th and 14th, so the decoder key is 140. 10th and 14th, eh? Okay, let's start with this. We could also do a display implementation, which will be easier for us. So we can implement one more trait here. We can impl display. We'll use the right macro f with a template string and self. So match self, fill match arms. This is going to be a list. This will be list, or this will be, we'll do this to string or num2 string. So here we can do list dot iter dot map v dot collect, which should give us a string. And providing that that's okay enough for us, we should be able to do print line here now. Or actually, that's the wrong one. It's up here. Print line packets, and then the vec is the issue here. So it's packets dot iter dot map v dot to string dot collect into a string. Okay, so now we go back to our display implementation now that that's working, and we do display for packet. If it is a list, we iterate over it, we map, we collect, and we have to we'll just take it the easy route and we'll do a format here with that value, collect it into a string, and we end up with all of these. I guess we should intersperse commas too, right? This, of course, is a nightly feature. So we go up to the top and we do, what is it? Hash, bang, feature, intersperse. Is that what it's called? Oh, I guess intersperse could work from itertools since we have itertools. But our issue is what? Expected string found string slice. That's fine. We can fix that to string. I forgot I had itertools in here. And then the warning we're getting here is probably that there's a nightly feature named intersperse. Yeah, here we go. So here's something that's really interesting. If I use intersperse from itertools, there's a warning here that says an associated function with this name might be added to the standard library in the future. And that's the nightly intersperse feature that we've used before. So it's really cool to get this warning both in our code and in the CLI. Okay, so we need to do all of that. And then when we do it here, I want to intersperse a new line. And this is our output. Copy that, throw it over here, copy this, search for it in this file, find out it doesn't exist, find out that the ordering is incorrect. So it should be this, right? And then 11311, which is way down here. So I think we wrote our comparison well enough to pass the test in the part 1, but not well enough to actually sort on. So maybe we write a test or two for comparison and we shore up our equality. Let's grab the right answer here and let's put this into a test, right? Where's part 2? Part 2 has a decent amount of code. I don't know that I really want to break all of this out. I think I'm fine just looking at it for now. So currently our first issue is that we get, this is sorted by numbers in our output. That's the issue. Well, that's not entirely true. It's sorted, empties are all first, which is fine. Then we have to compare. So all our chunks are all in the right spot. Like the individual pair comparisons are all in the right, I think. Like 11311, 11311, and 11511. That's not true for the empties because the 3 is next to an empty and it gets moved all the way up there. But in our current situation, a number is always less than a list, it looks like. So let's start with this. Let's start with debugging our ordering by doing a print line with self comp other. Now let's see if we can eke out all of the comparisons that are happening, which actually may never run. Oh no. Oh no. No, 63 is running. Okay. I have an idea. Let's go look at sort. T has to be ORD, so it has to be using ORD. So I'm going to go with it should be using this, but why am I not seeing output? So we do see a bunch of EQ, but we don't see any ORD. So I feel like this is using PartialOrd for some reason. Packets.sort. Let's do a sort by AB, a.comp b. And then did our test just pass? Okay, so sort doesn't use the ORD implementation? That is non-intuitive. Why would it not use the ORD implementation? Sort by. Okay, so the function sort requires that T implements ORD. If we look at this, it's a merge sort, but it uses a.ltb. LT is a PartialOrd implementation detail. So what happened here is our ORD and our PartialOrd, because I derived PartialOrd, don't match. Here's the warning here too. It's easy to accidentally make PartialOrd and ORD disagree by deriving some of the traits and manually implementing others. Okay, so we're gonna sort this out right now. Yes, I did just do that. So I'm going to define a function compare, and it's going to be a reference to a packet and another reference to a packet. So we have this CMP function, and instead of impl ord, we're going to do impl PartialOrd. We already have a PartialOrd derived, so I'm going to get rid of that. We're going to leave equality or EQ because it doesn't matter. We're going to look at ORD because they give us an example somewhere. Or I thought they gave us an example of deriving all three. I guess we have to do this, or we can do this anyway. Let's get rid of this little fakey function here. And then this is going to be packet. That's going to be ordering. And this is PartialOrd is going to be self.comp other. So it's going to be the same implementation, which should, if we cargo test, pass. And it does. So the lesson here is if you implement ORD, make sure that your PartialOrd agrees with ORD. And you can do that by making sure that you literally use ORD as the implementation for PartialOrd. That's all that was. So let's run part 2 and let's get rid of those print lines. Doing the display implementation was fun, but we do not need it. So I'm going to do that. I'm going to use 21756, and that is the right answer. So we were right all along. Our issue was that sort defaulted to using the LT function, which is a function on the PartialOrd trait, not the ORD implementation. So our PartialOrd and our ORD disagreed, which meant that we had confusing behavior. And this is one of the reasons it's really important to write a bunch of tests and make sure that you keep these things correct. Let's take a look at our ASCII art here, because there's a bridge here. So sweet. So part 2 is actually standing on the shoulders of part 1. We actually didn't need to do anything different than part 1, except make sure that our PartialOrd implementation for packet, as well as our ORD implementation for packet, matched. Once we did that, we got the pairs in the same way that we did for part 1. We defined our 2 separator packets. We collected all of our packets by flat mapping over the pairs, chaining packet 2 and packet 6 onto the iterator and collecting. So we got a vec of references to packets. We sorted them using our sort implementation. This is the function that used LT rather than using CMP. So once we got our PartialOrd and ORD in order, then we were able to do the find for each of the packets. This looks really strange. I'm sure it is because we're using references all the way down. So for example, we parse into a pair list. This owns the vec of pairs. This owns all of the pairs. Pair list does. So if we iterate over that, we get one reference, right? So left and right are references. So now when we flat map over them, we have an iterator of references to packets, not an iterator over packets. That's why we have packet 2 and packet 6 owned by these 2 variables up here, so that we can reference them into this chain. We sort all the references, and we have to then also iterate over the sorted packets. So now we've got a vec of packets, or references to packets, that we iterate over, which gives us another shared reference to the items. So we've got a double reference here. And then find also wants to take a shared reference to whatever it is that we're looking for, because we need the shared reference to do the comparison. And there's no reason to take ownership in find. And that's how we get 3 references here, because we take a reference, we take another reference, we take another reference. So if you're ever doing equality, the references on both sides really need to match in general. So when we end up with a packet that is a triple reference here, then we need to also have a triple reference on the right. And then because they're one indexed, we do add 1 to each of the indexes and we multiply them to string it, and everything works. So I'm actually generally very happy with this. It turns out very, I want to say something like idiomatic, but it just feels like Rust supports doing this very well. It supports grabbing these into enums. It supports things like the display implementation here that we wanted to print out. Although we wrote this kind of very haphazardly. We could probably write this implementation better. I'm constructing a lot of strings that I probably don't need to here. And then we get to implement these traits: partial equality, PartialOrd, and ORD, which defines all of the behavior that we need. And the implementations aren't even that complicated for us to write, because we are relying on the fact that Rust already has a lot of these implemented for the base data structures, and we're really just wrapping those base data structures. So this isn't a packet list, really. For our purposes, it's a vec. So I think that's it for today. I hope you enjoyed the video, and let me know what you did for this problem in the comments, and have a great rest of your day. I'll see you tomorrow.